Okay, this is the third part in the experiment. Um, I wanted to, like change the PowerPoint presentations to something, like what I do. It's just scribble down a lot of things, make sense of formulas, and then Google a lot, add it with some books. Wisdom of books is amazing. There's nothing like reading a classical thing, and the classical thing is not always like Dirac's principles of quantum mechanics. Sometimes it's digging into an original formulation of a criticism of someone like Lorenz, talking about the last Solvay conferences. He was part in. Fortunately, Hendrik Anton Lorenz died a bit too early. Einstein, I think he got tired of discussions. He really got tired. He died happily. Richard Feynman is, he was, I think, subject to constraints. I think that has been well documented in the movie. Oppenheimer, his biography is more interesting than the movie, the book on which the film is based. In any case, I wanna take you. I wanna continue this thing, and I wanna get over it. For me, the main thing is basically getting a bit acquainted with a new way of presenting things, using a blackboard like they use in Khan Academy or edX. Wonderful. I've did the courses on quantum mechanics on edX. They use this kind of stuff much more sophisticatedly than I do. So I wanted to go with a sort of a big bang, and that's to leave, 2, 3, 4 lectures like Feynman left at the end of his life. The Auckland lectures, which he then condensed into, this wonderful theory of light of matter, a little book which he didn't write himself, but was basically, a transcription by a scion of the lay family, not a scientist, a filmmaker. So, any case, that's 3 minutes into the game. That's too much. So I should get to the basics. I presented this first slide in my notebook, where I said the concepts you need to retain are these. Okay, let me move away the screen recorder here. I use something very cheap. Sorry for that. The concept of an efficient mass, if you talk about a very fundamental concept of charge. What is charge? We have charges and we have fields, and so if you think about charges, that's what I've presented so far. Is a charge is going to have a number of qualities. It cannot be something that it has no spatial dimension, whatever. It's going to move around in space. We think electrons and protons and their antimatter counterparts are actually charged oscillations, and the thing is, when you this is probably due to our way of thinking, when you think of thinking of a charge not as some continuous charge distribution, but as something that is very point-like, going around and around, then you arrive at an electron model which is the one I presented here, where you have an electron as the smallest smallest possible super conducting loop of an element of charge, theta-beweging charge, which has really all of the charge, the plus one or the minus one elementary charge that you have that happens to be associated with an electron. It's all condensed in a point, and it's not a point. It has a physical dimension. We talked about that. We think of this really as the classical electron. The radius of this point-like charge, as I said, it's not infinitesimally small. It is something. It is charge. So then we have our, Kantian concepts of time and space that we apply to it. Something that has zero dimension in space-time. And you can separate out time and space, but something that has zero dimension in space-time, it doesn't exist. So this zero charge must have some qualities, and we think some kind of rest mass is not part of it. But some kind of spatial extension is part of it, is part of what makes this concept of a theta-beweging charge real. And it does so through the anomaly in the magnetic moment, which we measured. I said it's something I'm not going to develop in this lecture. Well, for some part I am, but when you think about something going around, okay, and that something has a dimension in itself, and you can associate spin with it. It goes in this or that direction. This is what you would do in atomic molecular, in atomic orbital. We are not going to do that. We think it goes around, and it's like a small spherical or planar extension of charge. So the concept of charge density does apply to this thing here. But if you expand this situation into, an orbital, where you think of like, okay, fine, my center of mass is here, and my center of charge, of course, is also there. We're gonna have that's not good. We're gonna have here, we're gonna have a small area within this planar or spherical theta-beweging charge that is going to be like outside of our theoretical v is c radius, velocity, and our r is h bar divided by the mass of the electron divided by c. And so that if you add the surface of this thing, then you're going to arrive at something like, because we know that the classical electron radius, let me change color because this is quite important. The classical electron radius is alpha times, the Compton radius, which is equal to alpha times h bar divided the mass of the electron times c. Now, this area, which is like, charge that is outside of your theoretical Zeta-Beweging model, outside of your theoretical radius of h bar divided by mc. The surface area of this thing is about. I looked at it. I really applied very gross trigonometry. Is going to be about alpha divided by 8. I apply to calculate that. That's pretty advanced trigonometry. For very small angles, with sigma being very, 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 very small, which basically means 1 divided by 1 over 2 pi, whatever you have. You can equate it to your angle. So based on that, I have a difference between my gross estimation and the Schrödinger factor, which is alpha divided by 2 pi. That's the anomaly in the magnetic moment. No, 2 times pi is about, 3.14 times by 2, 6.3 something, 8. I think sort of that difference is good enough to sort of justify the theory that we have, that, the Zeta-Beweging charge has a finite spatial dimension, which relates to the quantum radius for interference between photons and electrons, which is of the order of alpha, the fine structure constant. And any aberration that we might have is due to the fact that if you think of a charge having some center of mass and having some center of a charge and oscillating around at exactly that radius that is given by these formulas, then you're gonna have an anomaly in the magnetic moment, and the anomaly is actually gonna be quite is not going to be intuitive. The anomaly, this is the amazing thing, is that the measured magnetic moment of an electron is actually slightly larger than what you would theoretically expect based on all the formulas that are here. So let me undo whatever I can undo here and move on. I can't undo more. Man, this must be the worst screen capture video ever. So the second one was this one. We refer to our second lecture. We say basically when you look at what's going to happen when this ring current is being observed in a real space. We often think about free space. Free space is not it's a theoretical concept, but it's very real at the same time. Free space is a very useful concept to think about that. In reality, an electron is going to move around a proton and hydrogen nucleus. There's going to be electromagnetic fields around. We're going to capture it in a panic trap. We're going to accelerate it in the Large Hadron Collider. It's going to move around, and we can find a wave function representation for it, which is not ideal, because it's gonna this wave function representation is just like, in general, we talk about probability amplitudes. Um, it's not perfect because it doesn't give us the exact position of the charge, the Titelbewegung charge, at any point in time or in space. It basically gives us a trajectory. It gives us, this is when you freeze space from, um, when you define a definite volume in space, and you have, the precise details on when our electron entered that space and when it left that space, or how it sort of keeps moving around in that space. We gonna have a wave function that represents the probability of where that thing is at any given point in space when we make time the variable, or at any given point in space when we fix time. And this wave function representation in that sense is very different, and at the same time so very much the same as an ordinary probability amplitude. And that is why Euler's function um, applies to both, where we can say, like, we can use Euler's wave function to represent a point-like charge, not infinitesimally small, but something that can be defined mathematically in terms of having a center of mass, having a center of charge, and going around at a certain speed, um, orbital speed and linear speed. And so that's where the things meet. The wave function of the wave function representation of our electron model just does meet the modern quantum mechanical definition of probability amplitude as a function that models where the thing might be at, or where, in which energy state the thing might be at. This lecture is not going very well, so let me move on and present you this thing that was even worse. We have a wave function representation of an electron, of a positron. The only thing that differs is the charge. We have, a representation of the argument of the wave function, which is here. Sorry. This Wacom tablet is really good, but sometimes you push on the button in the front to activate it or not activate it, and it brings up weird things. So we have a wave function that we can represent in our space. The E, Euler's number, is fixed. So the thing that varies is whether we want to, switch from our reference frame to the reference frame of the electron. When we think of the reference frame of the electron, we have this. When we think of our reference frame, we have this. The thing is, actually, it's not black and white. This is I think this is the most maybe from all of contributions of to all the weirdness, is that there's no thing okay, we're going to represent things in our frame of reference, or and there's no other possibility we're going to represent things in the other the rest frame. is when you talk about, and this is where these things feel very real to me, is that you can say like, okay, hey, the rest energy of an electron is the same in each reference frame. H is constant. Um, so then we indeed have like things that are relative. The relativistic energy that gets added to the rest energy, and we have momentum vector and x, and the thing is, the beautiful thing is that you can like switch and say like, especially taking into account that the wave function representation is more like a trajectory, it's more like a parametric a surface or a line curve in 2D, or it's a representation of where the particle is during some time in some volume of space when we let both time and space vary between two discrete values. It doesn't give us a representation of where the thing is right now, right here. And we can't, because we don't know the initial conditions of the system. We don't know whether this particle, at time t was here, or here, or here, or here. That we don't know. So we have a weird wave function representation. I completely ruled up my notebook, where it's very artificial actually. Where you say like, okay, fine, we have a frequency, right, and that frequency measures things in one plane. It's intimately linked to I, the imaginary unit, which can be +1 or -1. Here we have -1. Yeah, that's fine. And then we can sort of say like it moves in this direction, or it moves in that direction. And so our reference frame in terms of y, z, x, what is what, has been defined in terms of right-hand rules, for choosing the y based on your choice of the x and the z. That's all fine. But it sort of doesn't mean that that's going to be my next slide, where we can sort of okay, a positron and an electron meet, right? So we're gonna have, what we're gonna have? Okay, we're gonna have an electron. Sorry. We're gonna have an electron, right? This one here, spin up, moving in the plus y direction, the plus x direction. And now we're gonna have, because they collide, there must be one in the minus x direction, right? So they want to annihilate each other. It's going to take a while, unless they're spin up down, or spin up is the same. Because we can imagine that they sort of dance around, right? And sort of to annihilate each other, we know the electric magnetic field vector somehow, it needs to go in a big bang. So what is plus must be minus in the other frame. No, in the same frame. So what is going to happen exactly? So the spin up and spin down are going to come together. They're going to line up the magnetic moments. So spin up is, yeah, spin down indeed. Meanwhile, there is some time that is needed sort of to make sure that these magnetic moments are effectively lined up in a way where, I'm sorry, you can have this where the electric field vector and the magnetic field vector of this thing are gonna be, you know, exactly opposite. And then we have this big flash, and this big flash, which is gonna lead to, you know, a photon, which I represent here. And so we're gonna have, because I don't know, the energy has to go somewhere, we're gonna have not one photon, but we're gonna have two photons. And then when there's a linear element, we're gonna have three photons, two virtual ones, I would say, and one real one. But that's sort of what you're looking at. Let me try to erase as much as I can, because I do want to keep like the original blackboard. Well, the original blackboard is not going to amount to much. I said that the disadvantage of this representation is that, like, you know, x and t, you know, they're related to each other by this linear velocity being by being x, the velocity by t. So we can write all this stuff back in terms of let me erase it. You know, t and v are not two independent variables. They're just one. They're just one variable. Again, you know, the x position is the velocity times t. So x and t are given by v. So they're not independent, and this is where you cannot easily combine wave functions. So now I get to the last part of my presentation. I should have added another slide, but I didn't. Where let's first talk about this thing here. Feynman's diagram. I don't want to be critical of Feynman diagrams. I think you know, many people appreciated them. They basically you know, give rise to this thing which is called virtual particles. It's the W plus or minus and Z0 bosons in the Weinberg theory. It's quark-gluons. It's a lot of things. I think Feynman diagrams are useful, but you know, there's so many constraints with that come with it. The first one is that you know, a positron. Oh, here we have actually a presentation where there's a positron coming in and an electron going out. You know, time is negative. Time is not negative. So the wave function representations that you need, you know, for a positron or a proper electron, you need to sort of have, you know, a slightly different appreciation if you're gonna be using phi or phi. Yeah, I mean, I wrote it here. Sorry, phi, the complement of phi, or you know, some kind of antimatter counterpart representation of the wave function. This thing, you know, T said, matter particles, they don't move back in time. They just fucking don't. Sorry, my language. The basic thing is in motion. If we have T here, and we have the position of a particle here, you know, particle will do many crazy things. Yeah, okay. These things are not possible. It means basically that at some point of time t, you know, don't seem to be able to add it anymore. At some point of time t, this particle was at two very different positions at the same time. That's not a regular function, and it's also completely impossible, and it shows basically that time flows in one direction when you do what Kant, Einstein, in his special relativity sort of said basically, things move in space of time, and they can, as we see here, they can go from one position by reversing, their speed and reversing direction. They can arrive at exactly the same spot, right? This is the same spot at two different points in time. That's all possible, but this thing is not possible. So let me try to clean up my thing here. Well, that's me to clean up a lot, but I've exaggerated. So these Feynman diagrams are useful, but I think there's a lot of degrees of freedom, if you want to call it that way, that they imply, and some of these degrees of freedom in terms of chirality, parity, time symmetry are not possible because and at the same time there's a lot of, I'm going to talk about this thing here. This is very interesting about parity and time symmetry in what is called as a CPT symmetry, right? PT symmetry can be broken, but when you reverse time, things are okay. Let me put a big smiley on that one. Sorry for that. So yeah, Feynman diagrams, I'm not against them, but the way they're being used is sort of is the show that we have going on now. Everything is possible, and then nothing is possible. And we need a mass generation mechanism, and it sort of never ends. Let me go back to the logical flow. There hasn't been much of a logical flow. The weird symmetries that we have. Fermions are supposed to be, what is it, I spin 1/2 particles. And so when you're gonna move from one Cartesian representation to the other, it just doesn't stop. It really just doesn't stop. What we have to realize is that, we have a ZBB charge inside of an electron that may be orbiting, a proton in complicated orbitals, which all gonna, in the end respect the E is, a number of times, sorry. The energy in each of these complicated trajectories is gonna be an integral number of h times the frequency that you have in these various motions, which all add up to, provide the complexity of life and all the building blocks of the universe. Try to erase as much as possible. So there's a few more. Okay. So we have an electron model, and then the thing is, as I said, with wave functions, you can think about our world, matter, antimatter, and that's kind of remarkably easily. It all makes sense. The thing that is not easy is thinking about all of that dark matter and dark energy that is out there. And there maybe I want to return. I haven't discovered the return fetcher yet, but I want to do that. Is when we think about photons, we realize that a wave function will model, the electric field vector going actually, becoming smaller and larger, and the there's all these nice animations. But the thing is, the magnetic field factor lags the electric field factor by 90 degrees. What if we could, let me undo this thing here. What if we could imagine that, chirality is a much more complicated matter, and maybe there is a sort of, the electromagnetic force that we know is left-handed, depending on your definition on, coordinate frames, and a lot of other physical conventions, and, magnets, and direction of current going from, a current actually is negative charge in our world going from point X to Y, and we model it often as something, positive going in this direction where, it's basically fucking filling a hole. But taking into account all these constraints on and conventions that we have, is the bold thing that has never happened in physics is that, maybe, just maybe, all of that dark force or matter outside, maybe there's a right-handed electromagnet, if we call our force, where the magnetic field vector would precede by 90 degrees the electric field vector. And so that opens a whole can of worms where you think like, honestly, mainstream theorists are dismissing this realist interpretation of quantum mechanics because they say, well, it violates this and that, and Zitterboeing interpretation, I'll come back to that, can be explained by the Darwin term in the expansion of this or that equation. Really? I'm going back to this thing where, parity symmetry. If you look at a clock from the backside, your spin directions will change. We know there's more to it. We will still work with some kind of charge. So I said our wave function representation of an electron in, when we reverse the X, Y, or Z axis, we can work with that. It will just be a plus or minus sign. But there's subtle things going on in terms of, the way, the 3, 9, and 6 on this clock are being represented when you look at it. And you say like, okay, let's put that now before a mirror. So the mirror, I'll let you think to this one. The mirror might still preserve the rotational direction, or may not. I will tell you it will not. Left is right, left is right. But it will preserve, this weird reflection where we have maybe a motion within a motion. And that's where you go like, the classical analysis in terms of CPT symmetries, when parity and time symmetry gets broken, or when charge and parity symmetry gets broken, and then, well, with time, we can sort of mix it. And yeah, you can, and at the same time, you cannot, because these parity or symmetry, what's called, symmetry breaking particle reactions, like, hey guys, honestly, you're gonna invent new quantities to be preserved, like strangeness and other stuff, to actually explain a depth or lack of depth in your analysis of, how these fundamental 3D geometries really work, where indeed you can have what we have here, rotations within rotations, that polar vectors, axial vectors that do not necessarily translate easily into the kind of mathematical abstractions or simplifications that you make. And that's where the field is huge. But that's where I think mainstream interpretation of quantum physics is going to die. And the problem is, right now we're at the stage, and I'm going to conclude my lecture on that, is that the Tito-Boego interpretation of quantum mechanics, or this realist, is not breaking through. Why is not breaking through? Because we're, one of my best friends and colleagues, he has this proton model, where I say, like, yeah, fine, you need a secondary explanation to indeed justify, the 4 times h bar frequency relationship, which you then combine plus, c is h times n, and the mass energy, and you arrive at your radius. So he's sticking to this toroidal model. I'm sticking to more like something like this, where I can have. Let me choose another color. Computer is rather slow. Okay, let me choose another color. Where I'm thinking, like, I'm still thinking in terms of ring current, but the charge can move in another dimension, can move in and out of that circular race. It's also maybe the whole plane of oscillation can be like rotating about back and forth from some equilibrium position. And these questions aren't solved, and that sort of is why Tito-Boego theory isn't breaking through, because I feel like we're mainstream. All of our equations are like proved. We don't invoke virtual particles. Well, here I want to make an exception for that one, because maybe we have a positive and a negative energy state of I mean, we can analyze an electron and a positron in terms of negative and positive energy states, and we can sort of define a virtual photon as something that moves at almost light speed of light, or at the speed of light, because there's no energy left in the Tito-Boego motion of the charge itself, but it still carries the positive and the negative charge, and in that sense it's a neutral current. I'm sorry, I'm going totally overboard here, but it's maybe the thing to be done on a video like this. But so that's the situation we have where Tito-Boego theorists, I ruined my notebook, are like, we are fighting. I say, like, I think it must be something like this. The proton model. For the ring current model, we're all done, we're all fine. We are agreed on that. But we need a proton model. And I'm going like, my model is spherical because I think that the 4-factor here in this thing, ESM square, the energy is a multiple of h bar times the frequency. I arrive at the real, and there's an anomaly and as well, and I can explain that. But I arrive at a real charge radius of the proton, which is 4 times the h bar, which you see pop up, and when you talk about nuclear force theories. My thing is, yeah, that's fine. And sort of, where do I base it on? I have a ring current, and a ring current must have, some kind of spherical dimension because it goes around, oscillates, or else, there's something like this going on. But then we need to apply it, and that's actually mathematically equivalent also. When you apply, this third oscillator on the 2-dimensional oscillator that creates your ring current, we must arrive at something like this at the spherical scale rather than something like this, where, I know my colleague is going to be very angry. He's an academic. This is his model, and it's fine, but I don't think it's the final model. I don't think it explains the kind of spherical backing that you have going on in nucleus. But this thing checks all of the boxes in every other way, while my model, I'll be honest, does not when you apply a number of other things. So the truth must be something in between these two, or a combination of these two. But that prevents us from, breaking through. I'm at the last slide, but look at the think about these things, and look at my papers. I'm not let me go here actually. So I'm a nobody, okay? I'm really literally a nobody. But what I try to do is really like, I've got like 40 pages. I put some papers that I call lectures, and then the last thing I start to do is like mystery papers. 1 of 4. The magnetic anomaly. Can we explain it? Maybe, maybe not. Annihilation. How does charge really vanish? Is it there? Is the charge just the local charge and the global charge conservation law? Does it make sense? The proton yard ball puzzle. What is a circuit? What is sort of the trajectory of, that charge in a proton? These are complex intermediate vector bonds, virtual particles. Yeah, I said it. They make some sense. We can mathematically interpret, an electron and a positron when they come together, when all other forces, kinetic forces, are no longer there. We can imagine indeed that, a negative and a positive energy state merge into some kind of zero state. But it means that, the energy needs to go somewhere. And you will have these photons, gamma ray photons. But does this justify electroweak theory? I don't think so. So there's a lot of stuff around there. Can matter be made of light? And and this is the thing also. The uncertainty principle. It's fucking statistical determinism. We cannot know the initial conditions of these systems, and so we're making representations of them, and then we let them collide. And so there's a lot of stuff. So I would say like go there and tell me whether I'm right or wrong. One thing I would like you to challenge on is, and this I need your help maybe. Sorry for being slow. Zitterbewegung on Wikipedia. I want to show this article. And this is where you're being, according to me, fucking brainwashed. Sorry for my language. This is 50 years old. Schrödinger made the mistake that, for instance, the frequency or the radius or sort of that secondary motion, he had a factor 1/2 or a factor 2 here in this case, which he didn't get right. Because, he wasn't thinking this through in terms of, effective mass and kinetic component. And then it's sort of like this whole article is sort of some kind of, mainstream fascist, I wanted to say, but it's mainstream theorist. Say, well, this can be explained. This is horrible. It has never been observed directly. I mean, I explained just now the mass, the radius, magnetic moment of an electron moment, and here they say that the Zitterbeweging of a free relativistic particle has never been observed directly. I'm saying, like, my models, honestly, or our models, because this is not developed in isolation, is the predictive capability, the match between our theory and reality is pretty close to perfect. And they still talk about, it's related to the Darwin term, a small correction, the lamp shift, right? Okay, the lamp shift comes out of our theory as well. This makes me sick. Interpretation, it vanishes on taking expectation values for wave packets that are made up entirely of positive or entirely negative energy waves. Yeah, of course, that's what we're talking about, particle and matter and antimatter annihilation, where you can say, like, yeah, our the rotation, the energy that is in the rotation, the orbital energy vanishes. And where does it go? Well, it goes into opposite photons. So this article, and I tried to influence it a little bit 2-3 years ago, and I got shut out. Wikipedia, I will tell you one thing. It's great when you want to know about mainstream theory. It's perfect. Just go there and get lost. Okay, that's what I do. Mainstream theory is not getting anywhere. It is not. There's many, academics and writers who say, like, yeah, we must make some choices, and we must go back to the founding fathers, and do something else. So I don't know. It's sort of I talked to some people, and David Hestenes is really, he single-handedly revived this whole interpretation of Schrödinger of what an electron actually is. And in the 1990s, I admire him a lot. I also admire a lot of other people. I said I'm just an amateur physicist, but the research group around Celani, Vassallo, Di Tommaso, they've been in cold fusion theory. They're doing well, they get paid at good universities, but they don't break through. And they don't break through because I'm sorry to say there is a mindset where mainstream theory is mainstream theory, and if you don't belong, then you don't belong. And so I don't belong, and I don't worry about it. For the other people, it's much more serious. I'm also thinking about some young academics like Oliver Konsa. I'm also thinking about some older Russian scientists who are currently being frozen out because of the conflict with Russia. It's not a great situation. And, the only thing is that what I ask you is to think for yourself And the one thing I do want to attack is, really this 50-year-old presentation of what Schrödinger's brilliant insight was all about. And that's not good. It's not about me. But when Einstein and Schrödinger, Dirac, these people, we need to keep their memories alive. And yeah, if you can make them a little bit greater than they are very great already, then I think you will be a little bit greater yourself. Okay, I'll upload this and then I will see what comes out of it.